For t greater than 0, unit step is 1. So out here, we just get the decaying exponential. Okay, so a is positive in this case. So to plug this into our Fourier transform expression, again, we're just going to integrate the exponential from 0 to infinity. All right? And here's what we get for an answer. And I'll show you how to get that. So, like I said, you get the integral from 0 to infinity of e to the minus at e to the minus j 2 pi f t dt. And when you combine the exponentials, you get a very easy integral to do, and I think it's pretty easy to see is that this is what you're going to get for the result. There's an important little detail in here in that a is positive, so that when you evaluate the exponent at infinity, you get 0, because this will dominate. Okay, so this should look like a very familiar quantity here, and we'll get to that in just a second. Okay, so here's some interesting properties of spectra. None of these should be a surprise. We have a Parseval's theorem. So signal power is it has roughly the same expression except for the magnitude. In either the time domain or frequency domain, they look very, very simple. So you can calculate power in the frequency domain or time domain, whichever is easier. And if you decide one integral looks very hard, you can use the Fourier transform to go into the other domain and see if the integral looks simpler over there. You play that kind of game all the time because of the Fourier transform's properties. And we have conjugate symmetry for real valued signals. And again, if it's even, the spectrum is even. If it's odd, signal in the time domain is odd. It's odd in the frequency domain. And furthermore, because of the conjugate symmetry properties, it's either real or imaginary, depending if the time domain version is even or odd. No real surprises there. You should be able to prove these yourself quite easily. Let's go into some more interesting Fourier transform properties. Okay. First one is one that you've seen before, and that if I delay in the time domain, that corresponds to multiplying in the frequency domain by e to the minus j 2 pi f times the delay. Okay. We've seen this with the Fourier series, and I think it's pretty easy to see when you plug that same formula, use the same mathematics in this case too. However, what's really interesting is what happens if you delay in frequency. You take the spectrum and shift it over by f0. Because these two formulas are so similar, you know that the answer has to be it's multiplied by a complex exponential. However, because of this sign difference in this formula, it's e to the plus here. So delaying in frequency corresponds to multiplying in the time domain by e to the plus j2 pi f naught t. Whereas if you delay in time, it corresponds to multiplying by e to the minus j2 pi f tau. Okay. So this is where you can really use to your advantage these symmetry properties, the fact that these look so similar. You can mathematically, if you can derive one property in one domain, you can use it to see what happens in kind of the reverse sense. Okay. Let's explore another property here, and this one is really easy, in that the signal at the origin in the time domain, its value at the origin, has to be the integral of the spectrum over all frequency. And the way to see that is to take this formula and just replace this by 0. Well, the complex exponential of 0 is just 1, And so you just left with the integral. That's pretty easy to see. And of course, use the same thing over here and just replace f at 0. So the value of the spectrum at the origin is equal to the integral of the signal. And here's one that's a bit more exciting. The spectrum of the derivative of a signal is j2 pi f times the spectrum of the original signal S. Okay, now how do you derive that? And the answer is, I'm simply going to take the derivative of this formula. So, d little s of t by dt is equal to okay. So what I'm going to do is I'm going to take this derivative and move it inside the integral. The only place that t occurs is right there in that complex exponential. Well, the derivative of complex exponential is just j2 pi f times the complex exponential. Times e to the plus j2 pi f t dt. Well, this is the inverse Fourier transform formula. However, what it has in it, what you're taking the inverse transform of is that, so that means these are related to each other. So, really pretty cool in that if you take a spectrum and you multiply it by j2 pi f, that corresponds in the time domain to taking a derivative. Very interesting. Well, if multiplying by j2 pi f corresponds to taking a derivative, guess what dividing by j2 pi f corresponds to? Well, that's got to correspond to integration. And again, you can show that by plugging this into the formula over here. I'll let you do that. It's pretty easy. And you can easily see that this is the way it works. I have a little question for you. What happens, what is the spectrum of the second derivative of a signal? What's the spectrum of the second derivative of a signal? So, ds over t, well, that's just the derivative of the derivative, right? So, the spectrum of this thing is j2 pi f. The spectrum corresponding to this is going to be to multiply it by another j2 pi f. And so what you get is minus 4 pi squared f squared times s of f. Okay, the minus sign, of course, is j squared. So you can also talk about the double integral of a signal, if you will, integrating it twice and all that. That corresponds to dividing twice by j2 pi f. Really interesting properties. So here's the summary of all those examples and properties that I've done in the previous slides. And they're very important for us. And we will use these properties over and over and over again. For the example that's coming up, it's going to be particularly important to remember the integral one and to remember this. We'll see that in just a second. And I guess that one's going to be important for me. First, I want to talk about a very interesting case that's very important. What is the spectrum of 1 plus a signal times a cosine? Okay. And S here is assumed to be a non-periodic signal. It has no special properties other than it's some signal. In fact, it could be something like a speech signal or something. So, first of all, we note that if you just multiply everything through, that we have a periodic part and we have a non-periodic part. The reason that this is non-periodic, the cosine may be periodic, but once you multiply by something that's not periodic, you get something that is clearly not going to be periodic. Okay. So, how do you find the spectrum of this? The way you do it is you use the Fourier series for the periodic part, and that we know what to do. That gives you terms only at plus and minus fc. We'll see that in just a second. And we're going to use the Fourier transform on the non-periodic part. And then, because the Fourier transform is linear, the integral of the sum is the sum of the intervals, so it's easily seen to be linear. We're going to add the results together. Our only work is going to be on this second term out here. Okay. So, I don't like doing integrals. I like using the properties. And the way to get at those properties is through Euler's formula. Of course, Euler's formula comes up a lot, and there's a reason for that. It's very, very useful. So, cosine is e to the plus e to the minus, and I'll put the s and t inside. Well, from our properties, we know that when you multiply in the time domain by a complex exponential, that corresponds to a delay or an advance in the frequency domain. And that's what each of these terms is. So you write